In this lesson, we're going to take a look at molecular shape, which we actually derive by looking at how the electrons are interacting, or the valence electrons are interacting. And that gives rise to this thing we call valence shell electron pair repulsion theory, which actually just allows us to use electrons and their mutual repulsion for each other to predict what's going to happen. Now, we're going to have to look at two different things. We're going to look at electron group geometry and molecular geometry. Molecular geometry includes the atoms that are stuck on the ends of bonds, whereas electron group geometry just talks about the electrons around a central atom. So there's a lot of information in here, but let's just go ahead and jump into what we mean by electron groups and molecules. So an electron group is a single pair of electrons, which we call a lone pair. Could be a single bond, a double bond, or a triple bond. These all count as one electron group. So here on our central atom, there are two electron groups, and a single bond and a second single bond. On this central atom, there are again two electron groups, but those electron groups consist of double bonds. Now you'll notice that these electron groups are getting as far away from each other as possible because electrons have a negative charge, they repel. And as far away as possible with two electron groups is 180 degrees, straight line. Same thing up here. These ones on the outside, these all have four electron groups. There's an electron group, there's an electron group, there's an electron group, there's an electron group. This one has three electron groups, the two lone pairs and that double bond there in the middle. But when we're looking at molecular structure and shape, we are interested in the central atoms most of the time. So let's look at electron group geometry when we have different amounts of groups. If we have two electron groups, they line up linear, like I just showed, where you have an atom in the middle and then the electron groups go to opposite sides. If you were to add a third electron group to that, it comes in here, but that actually pushes these two things away from this one, right? We want to have every angle the same, so they're as far away from each other as possible, which actually puts them at 120 degree angles off the central atom. These are still in a plane, okay? And what I mean in a plane, I mean they'd all fit in one dimension. It's kind of flat. But when we go into four electron groups, then we get tetrahedral geometry, and this is not a plane. Tetrahedral is actually a three-dimensional shape. So let me show you a tetrahedron. Okay? This is a central atom with four electron groups going around it. And you can see it sticks out in three dimensions. And no matter which way I rotate that thing, there's going to be 109.5 degrees between each one of these legs. So if I go from here to the center of the sphere to here, it's 109 degrees. Or from here to the center of the sphere to here, it's 109 degrees. Or from here to the center of the sphere to here, it's 109 degrees. So this is tetrahedral shaped, and the reason we call it a tetrahedron is because if you actually connect up the four corners from here to here to here to here back up to here, that gives you four sides on this solid. Each side is a triangle. So tetrahedral is a triangular solid of four sides. Five electron groups is Trigonal Bipyramidal. It's also a three-dimensional shape. We'll look at a cartoon of it in a minute. But imagine you had a pyramid that had a triangular base instead of a square base. Then every side would come up and there would be a point here. If you put another one of those behind it so that the base was in the middle and had 2 points coming off of it, you'd have Trigonal Bipyramidal. And then if you took octahedral, which is 6 electron group, instead of a triangular pyramid, you have a square pyramid. Again, you have 1 point coming up and 1 point would go into the paper behind it. So you get this octahedral shape. It's got 8 sides. So let's take a look at some cartoons of these things and what happens to make molecular geometry different than electronic geometry. The electronic and molecular geometries will be the same as long as every electron group is a bond. But if there's lone pairs, then the molecular geometry will be different. So we start with linear, which we've looked at. Here's CO2. It's nice and linear because the central atom has two electron pairs on it, two electron groups on it, and they line up 180 degrees away from each other. Trigonal planar, 3, and they line up in this orientation, so they're all equally spaced as far apart from each other as they can get. Then we move into the ones that get a little bit more interesting, where we get tetrahedral, and I showed you this. Oh, and over here, since now we're in 3 dimensions, we have this thing, which is like a Lewis structure and yet not, right? The Lewis structure for this would look like carbon, single bonded to hydrogen, single bonded to hydrogen, single bonded to hydrogen, single bonded to hydrogen. And it makes it look like this is a planar thing, then it's all in those page. This wedge and dash and line method lets us see that these are actually three-dimensional things, where you read dashes as in the plane of the page, wedges as coming out of the page, and dashes as going behind the page. So that actually tells us this hydrogen is behind the page, this one's in front, these two are in the page, and we get this tetrahedral shape. And we're going to look at what happens when our electron groups and bonds are different in a minute. Here's Trigonal Bipyramidal. Here's that three-sided triangle in the middle, and then if you trace it up to the peak every time, then you get that trigonal pyramid or triangular pyramid, and then the bottom side has that as well, and so you end up trigonal in the middle, bipyramidal off of both sides. And here's the dash line wedge, or dash line wedge diagram for that. You can see you have this triangular thing in a plane. It's going into and out of the page, and then you have the points going up and down off of that shape. And then if we look at octahedral, you can see here's your square in the middle, and then you have pyramid if you connect up each corner of the square to the top one, and then you have your second pyramid if you connect down here, and since this is an 8-sided figure, we call it an octahedron. So now, what happens if some of these atoms stuck on here with a bond are actually not bonds but just lone pairs of electrons? That's going to change the shape of our molecule, but it doesn't change the electron group geometry, it just changes the molecular geometry. So let's take a look at that. Ammonia is NH3, but you'll notice ammonia actually has this lone pair. So it has 4 electron groups, which means we know it's tetrahedral. But because this electron group is essentially invisible because there's no atom stuck on up here, we mostly just care about these 3. And so we don't have a full tetrahedron. What we have is trigonal pyramidal. Trigonal pyramidal, which is a subtle difference, but it is a difference. It's not quite tetrahedral. So the molecular geometry is different because there's not another atom up here to make it a true tetrahedron. Water is another good example. Here is tetrahedral electron group geometry because we have 4 of them, but these 2 electron groups that are coming off here and here are invisible to this, so that pushes these single bonds around and makes this molecular geometry bent, and that allows this oxygen to actually pull the electrons from hydrogen closer to it and give it a partial negative charge and our partial positive over here. So the shapes of these molecules actually give rise to the polarity, and that together with the bonds. So we're going to put these all on a chart. This one summarizes what's going to happen. So the least amount of electron groups we can have is 2. We have 2 double bonds coming off, and that's going to be linear. And there will never be lone pairs when we have that. Carbon dioxide is a nice example. If we have 3 electron groups, then we might have all molecules or all atoms stuck to the end, in which case we are going to have trigonal planar. Or we might have 1 lone pair of electrons over here, which is going to give us a bent configuration. Sulfur dioxide shows us a bent configuration. So the molecular geometry is bent, even though the electronic geometry is trigonal planar, because this third group coming off over here is electrons, and it's invisible in the molecule. Moving on to a tetrahedral electron geometry, we can have 0 lone pairs, 1 lone pair, or 2 lone pairs. If we have 0 lone pairs, then of course our molecular geometry matches our electronic geometry and everything's a tetrahedral. Like I mentioned earlier, if we have 1 lone pair, that takes care of the top piece, and so we get trigonal pyramidal. If we have 2 lone pairs, then we end up with bent, like water, like we looked at before. If we move on to 5 electron group geometry, remember this is trigonal bipyramidal because you have the triangular plane and then pyramids coming off of both sides. If we get rid of one of those one of the atoms and make it a lone pair, so we have 1 lone pair, then our molecular geometry changes from trigonal bipyramidal to what we call seesaw. And the reason we call it seesaw is if you imagine this thing, these are the legs coming off of the bottom, and this is the 2 atoms that are bonded, and this thing could rock back and forth on those legs, and we don't see those in the molecule. Those are just electrons. If we eliminate another pair and we have 2 lone pairs, then we end up with a shape called T-shaped, because that's what we get when we look at just the terminal atoms coming off of that central atom. We ignore these. And if we have 3 lone pairs, then we are back to a linear shape because we've eliminated the 2 legs and the person on top, so we just have a nice line. Then if we move into octahedral geometry, which means we have 6 electron groups, if we have no lone pairs, then the molecule and the electronic geometry match. If we have 1 lone pair, then we get square pyramidal, because we had octahedral, which was 2 square pyramids stacked on top of each other, but if we eliminate the point off one of them, then we have a square pyramid. If we eliminate two lone groups, then we have eliminated the pyramid off the top and off the bottom, and we end up with 4 atoms, in a plane.